This little video is to just take you through the handout or the guide on mass defect calculations. You can just use the PDF and skip your way through, but you might want an explanation to help you on the way. We're just going to start off with what we've done already, which is the fact that mass defect is the difference between the mass of an atom and its constituent nucleons, and it's equivalent to the mass equivalent of the binding energy. Okay, and that's because the mass of any particular nucleus of an atom is always less than the mass of its component nucleons, its protons and neutrons. And so an example, the mass of an oxygen-16 nucleus, which contains 8 protons and 8 neutrons, is actually less than the mass of 8 separate protons and neutrons, protons being red in this case and neutrons being orange. So there you go, the mass of the nucleus is actually less than the mass of just those same 16 nucleons, 8 protons, 8 neutrons, if they're on their own. And that's because, okay, when the nucleus comes together, as those proton and neutrons come together and the strong nuclear force grabs them and pulls them together, they lose some mass and they release some energy. So some of their energy is lost. And we call that energy the binding energy because you've got to put that energy back in order to separate the nucleons back out again from the nucleus. However, though, even though mass defect should be formally talking about a single atom and the difference between the mass of that single atom and its component nucleons, sometimes mass defect is incorrectly, I suppose you could say, used to refer to the change in mass during a nuclear reaction. Let's have a look at that now. So this so-called mass defect of a nuclear reaction can actually be used, though, to calculate the energy released in any given nuclear reaction. So mass defect, we're going to call it delta M, of a nuclear reaction is just given by the mass of the products, take away the mass of reactants, and just like in chemistry, in any reaction, reactants are the things you start with and the products are the things you finish with. So the mass defect is the mass of the products, take away the mass of the reactants. And we can calculate energy release from that, similar to how we calculated the binding energy in the mass defect of a single atom, because if we've got a mass defect, a change in mass measured in kilograms, we can use E equals minus delta MC squared to calculate the energy released from that nuclear reaction. That'll come out in joules. Or if we're being sensible and we record our change in mass in atomic mass units, or U, we can use that equation E equals minus 931.5 times that change in mass, and that'll give us our answer in mega electron volts. But you might be asking a question, wait a minute, where did this little negative sign come from? So why the negative sign? And that's just because energy is released when mass is lost. And because change in mass in this case is the mass of the products minus the mass of reactants, if mass has been lost, that means the change in mass of the reaction will be negative because mass has been lost. But we want to represent that as a positive energy value. So we say when mass is lost, energy is released. So the negative sign in there is just to remind us that when mass is lost, energy is released. So when we get a negative delta M or a negative mass defect, which means mass is lost, that means we get a positive number for energy because we know that energy is coming out. So it's just a little mathematical thing to make sure our numbers sort of make sense when you're looking at them. But just be aware, depending on the textbook, some textbooks have a negative sign, some textbooks don't. Some textbooks, when you get a negative energy, that means energy is lost. Some textbooks, when you get a positive energy, that means energy is lost. It doesn't really matter at the end of the day. What matters is you understand that when mass is lost in a reaction, energy must be released. That's the key thing for you to understand. And so let's have a look at some examples of how to do this. This is what you'll be doing in the worksheet after you finish this. So this is an example. Calculate the energy released for this nuclear reaction. So you've got fluorine 19 reacting with hydrogen 1, and they're turning into oxygen-16 and helium-4. So I've got it in very simple terms, but also the nuclear notation on the right-hand side. And the question has given us some data. We've got the masses of fluorine 19, hydrogen 1, oxygen-16, and helium-4. So how do we go about figuring out how much energy is released in that particular nuclear reaction? Well, first of all, we figure out the mass of products. And the products in this case are obviously oxygen-16 and helium-14. Okay, the products are the things we produce, so here they are here. Okay, they're the products of the reaction. We figure out their mass. And it's pretty easy to figure out their mass. We just add the two masses together, which is roughly 16 and roughly 4. So the mass of those products is about 20 atomic mass units. The next step is we figure out the mass of the reactants. And once again, that's pretty straightforward. The reactants are the things we start with. That's our fluorine 19 and our hydrogen 1. They're our reactants. And we add their masses together, which is roughly 19 and roughly 1. And we find the reactants have that mass as well, which is pretty close to the other mass. So the mass change isn't very big. But step 3 is actually figure out the mass defect, the change in mass, which is the mass of the products, take away mass of reactants. In this case, it's the mass of the products, which is 20.0026, take away the mass of the reactants, 20.01233, and we find that there is a minus 0.00973 atomic mass unit mass defect, which means mass has been lost in this reaction. As we know, if mass is lost, that means energy is released. So step 4 is calculating the energy release. And we can, because we've got atomic mass units, we can use that nice shortcut and it's minus 931.5 times that mass defect. So it's minus 931.5 times minus 0.00973. And because we're using atomic mass units, we know our answer is going to come out in mega electron volts. So 9.06396 mega electron volts. And that's how much energy is released every time one fluorine-19 atom and one hydrogen-1 atom react to form an oxygen-16 and a helium-4. And that's how you calculate the energy release from a nuclear reaction using this slightly incorrect concept called mass defect. All right, let's have a look at some more examples, shall we? Actually, no, there's some questions for you to try. So what I've got here is 2 questions. If you're listening to the video, you could always pause it here, have a go at these yourself, then follow on and see if you can check your answers as you go. The first one goes back to the real mass defect. It's actually calculating the mass defect of a single atom, and there's 3 questions to calculate for this copper-63. What's the mass defect? Therefore, what's the binding energy? And something new, what's the binding energy per nucleon, which means how much energy is associated with each of those nucleons in the nucleus. I'll let you think about that while you're trying to solve that one. And the second question is just like one we just done. I've given you a nuclear reaction. You've got to figure out the energy change during that nuclear reaction. So pause the video now, please. Have a go, and then you can play it again or look at the PDF and look at the answers. Okay, here we go. First question. Okay, first question we have step 1. We're trying to figure out the mass defect of copper-63. We've got to figure out how many protons and neutrons it actually has in order to figure out what mass it should have. So first of all, it's for copper from the periodic table has an atomic number of 29. Therefore, it must have 29 protons. To find the number of neutrons, we have the mass take away the number of protons, and we get 34 neutrons. Just be careful. Don't look at the periodic table necessarily to figure out the number of neutrons. If they've told you this copper is copper-63, that means the mass of this copper is 63. So when you calculate the neutrons, you must use 63, regardless of what the periodic table says. This isotope is copper-63, so you've got to use that number. So now we've got 29 protons, 34 neutrons. We can now do step number 2. What mass should these nucleons have if they were freely floating around in space, not in a nucleus? What mass should they have? We can do that pretty easily. It's just 29 lots of the mass of a proton, which they've given us up above, and 34 times the mass of a neutron, which they've given us up above. And so, in theory, the mass of these protons and neutrons should be 63.50590 atomic mass units. But now we can find the mass defect. So, the mass defect of a nucleus is the mass of the nucleons minus the mass of the nucleus. We've been given the mass, we calculated the mass of the nucleons, 63.50590. We were given the mass of the actual nucleus, 62.91367. So it turns out there's actually a 0.59223 mass defect. The nucleus weighs a considerable amount less than the actual separate nucleons. So now we can turn that into a binding energy, and you'll get the mass defect. To find the binding energy, it's just 931.5 times the mass defect. Notice there's no negative sign here because of the way we've defined mass defect when it comes to a single atom. And what we find out is that when we do that 931.5 calculation, we get the binding energy of that nucleus is 555.76 mega electron volts. And now we can do this new thing called the binding energy per nucleon. It's essentially how much binding energy or how much mass on average has every nucleon lost. And it's pretty simple to calculate. You just take the total binding energy, and because it says per nucleon, you just divide it by how many nucleons you've got. And we know there's 63 nucleons inside copper-63. Obviously, the name already says it. It's copper-63, therefore it's got a mass of 63. Therefore, it's 63 nucleons. But just to prove it to yourself, you can add the protons and neutrons together and also come up with 63. And the binding energy per nucleon is just the total binding energy divided by the number of nucleons. So it's that 555.76 divided by 63, or 8.82 mega electron volts. That means every nucleon has a binding energy associated with it of 8.82 mega electron volts, or every nucleon has lost that equivalent amount of mass to 8.82 mega electron volts. And you've got to supply that to those nucleons to get them back to being free again. On to question 2. Calculate the energy released during that reaction. Let's go through this nice and quick. First of all, what's the mass of the products? In this case, the products being the things we're making, thorium-234 and helium-4. We've been given the data, so it's easy to calculate their mass. The mass of the products is that number there, 238.0462. Step number 2, what's the mass of the reactants? Well, there's only one reactant in this case. It's just the uranium-238, and therefore the data just gives us that mass. That's nice and easy. What's the mass defect? It's the products take away the reactants, and therefore we can find 238.0462 minus 238.050786. We have a negative mass defect, which means mass has been lost, and we all know that means that energy has to be released. So now we use that equation with a negative sign in there. It's minus 931.5 times by the change in mass, or the mass defect, and we can figure that out as 4.3 MeV is the energy release for this particular reaction. And that's a nice quick run through of how to do mass defect calculations you're free to go ahead and try some on your own from the worksheet now.